Welcome back to Arts Learning. In this video, we'll be going over momentum and starting off our momentum and impulse force time units. Force time unit, okay? So first, we're going to start off with momentum as a vector, what it really means, and we're going to cover more in this video, which includes impulse as well as force time situations. So first, what is the quantity of motion? What even is this quantity called momentum, right? So you might have heard multiple times in a movie or something, right? When they're swinging around, that if somebody's swinging around very fastly, he has more momentum, right? Suppose he's on a rope, and if he needs to get to this cliff, he needs momentum. So he swings around, he keeps swinging around, he gets more momentum, and he jumps here. You might have heard this term thrown around a lot, right? Momentum, you need more momentum. If you have momentum, you're unstoppable, all that. But what is it physically? What is it as a quantity of physics? It's P is equal to M times V. P here is the denotion of momentum, okay? M, mass, and V is velocity. So it's kgs times meter per second, which we also know as Newton seconds. This is another way to denote it, Newton seconds, okay? Because Newton is just a kilogram meter per second squared. If you multiply that by a second, you'll just get kilogram meter per second, like this. So that's what momentum is, all right? If you have a higher mass, you'll accordingly have a higher momentum. If your velocity is higher, you'll also have a higher momentum, okay? So if you have a lot of mass, you'll have a large momentum. If you have a lot of velocity, even if you don't have a lot of mass, you'll have a lot of momentum, which makes sense, right? You wouldn't want a rhinoceros coming at you, even though it has a low speed, right? Because it has a lot of mass. If it hits you, you're still going to get hurt. And you don't want a bullet coming at you, even though it has a very little mass, because it has a huge velocity. And it's going to pierce through you, right? So momentum is directly related to mass and velocity. And it is not energy, right? Energy is measured in joules. And also, if you double the velocity, then the momentum becomes doubled, but the energy becomes quadrupled, right? Because it increases as a factor of v squared. So kinetic energy is not the same as momentum. Momentum is how much punch you have, how much, how hard you can hit. And momentum is a vector quantity, okay? So I'll put this denotation here. If you go to the right, you can have a positive momentum. If you go to the left, you'll have a negative momentum. Okay, pretty simple. This is the common denotation. It could be left is positive, right is negative, but this is the common denotation. Okay, so let's try cases, right? A 1500 kg car moves right at 20 meters per second. What is the momentum of this car? So that's just the mass. Momentum is equal to mass, 1500, times velocity, which is 20 meters per second. Kgs here. 1500 times 20 is 30,000 kg meter per second. Okay, so 30,000 kilogram meter per second, or Newton seconds. This could also be written as Newton seconds, but same thing, right? Now here, the same 1500 kg car moves left at 20 meters per second. Okay, so this car is now moving left, which we define as the negative direction. So what's going to happen? 1500 times kgs times negative 20 meters per second, or negative 30,000 kg meter per second. Oops, not 300,000 kg meter per second. Okay, so momentum is a vector quantity, okay? Unlike energy, but similar to force, has a direction, okay? Now, which has more momentum? A fly with a very small mass, 4 times 10 to the negative 5, but a very high speed, 2.5 times 10 to the 5, or a truck with a mass of 2,000 kgs, but with a speed of only 0.004. So if you multiply the fly here, 10 to the negative 5 and 10 to the 5 cancel out, 4 times 2.5, or 10 kg meter per second. That's its momentum. If you multiply the truck here, 2,000 times 0.004, or 8 kg meter per second. So the fly, you wouldn't think it, right? You would probably want to be hit by the fly, because you wouldn't think a fly would be so harmful. You'd probably avoid the truck, but the truck actually has lesser momentum here because its velocity is lower. But here we have a high velocity and a low mass. Okay, so let's try these problems. Find the momentum of a 0.5 kg ball moving right at 12 meters per second. P is equal to m, 0.5 kgs, times v, 12 meters per second, which is 6 Newton seconds. The momentum of a 70 kg runner moving leftward at 8 meters per second. Okay, so here that's the trick. It's a negative, right? Because we define negative as left as a negative direction. So 70 kgs, I would say, and then velocity, since it's a vector quantity, negative 8 meters per second, which would give me negative 560 Newton seconds. A 0.2 kg bird has a momentum of p is equal to 3 Newton seconds, or a kg meter per second. Find its speed. So momentum, right, 3 kg meter per second is equal to m, so 0.2 kgs, times the velocity. So the velocity is equal to 3 kg meter per second divided by 0.2 kgs. Kgs cancel out. You're left with 3 divided by 0.2, or 15 meters per second. Okay? And since it's asking for speed, we don't really care about the direction, right? Speed is just the magnitude, and this is our magnitude here. Okay. Object A is 3 kgs at 4 meters per second, and object B is 2 kgs at 6 meters per second. Which has more momentum? Object A is 3 kgs times 4 meters per second is our momentum, which is 12 Newton seconds. Okay. Object B is 2 kgs times 6 meters per second, which is also 12 meters per second. So 12 kg meter per second, or Newton seconds. Both of them are the same. So this just goes to demonstrate how even if an object has a larger mass, it still has the same momentum. It still packs the same punch as an object with a higher velocity. So these are more basic questions to get you more incorporated with the concept, but we're going to ramp it up soon, okay? Next session we'll be going over, next video we'll be going over 2D and 3D momentum. Only 2D, but 3D we'll just discuss a bit. So first, after this, let's look at impulse and the impulse momentum theorem. Okay? So what does that even mean here? Impulse, this is a new quantity we haven't heard of, right? Whoops. Impulse is defined as J. So these are weird quantities, right? Momentum is P, because you can't say M for momentum because that's mass, right? J, same thing. Impulse, I is taken by, I forgot, it was some other quantity. Oh yeah, it was current. Yeah, it was current. But J is what you're going to use for impulse, okay? And that's measured in force times delta time. Now, the units these give you is Newton seconds, right? Which is the same units as the momentum. So are they the same thing? No. Okay. Impulse is the change in momentum. So this is one formula for impulse, but it's also this. J is equal to delta P, which is m times v final minus m times v initial, okay? It's the change in momentum. Because impulse is a totally different quantity. It's how much force you sustain over a specific amount of time, okay? So if that time is lower, it'll have a larger force. If time is force. So I'll go over that a bit more in detail right now. But let's just get introduced to the concept, okay? Impulse is not momentum. It's not directly equal to momentum. It's change in momentum. The delta is important here. Delta M, delta P. Okay? So there's two quantities that define it. Force times delta time and delta P. So a big force for a short time, like a sudden car crash, can equal a small force for a long time. Like, well, I don't know, maybe you're just pushing on something for a long time. Okay? They have the same impulse. So, yeah, J is delta P. That's the main key takeaway here, okay? Impulse is how fast something happens, the change in momentum. How fast does your momentum change? How fastly are you incurring that damage? How fastly is something happening, right? Not something, how fast is something happening, that's the wrong term, but how fast do you sustain or change your force and your momentum? Okay. So let's look at an example of what this could look like. All right. A 0.15 kg baseball, mass is equal to 0.15, approaches a bat at 40 meters per second and leaves at 50 meters per second the other way. So 40 meters per second is velocity initial, right? Because it approaches at 40 meters per second. And it leaves at 50 meters per second in the opposite direction, which means its velocity final is 50 meters per second. Its mass will still stay the same, right? Because it's the same object. And now we need to find the impulse. How are we going to find that? Well, impulse, J, is equal to delta P. So what is our delta P here? That's our P final minus our P initial. Our P final here is 0.15 times 50 meters per second, right? So this whole Newton seconds minus P initial, which is same 0.15 times 40. Or 1.5. So 0.15 times 50, right? And then 0.15 times 40, we can do 0.15 times 50 minus negative 40, right? Because thing is, here, see what happens. It's leaving in a different direction, right? So we can consider negative 40 meters per second to be the direction it's happening in. The direction it's getting thrown in, okay? The ball is going this way first, and then it's hit by the bat. Then it goes the other way. And so its impulse will be in two different directions, right? So I could either consider this to be negative or this to be negative. Since I usually go with rightward is positive, I'll consider this to be positive, and its initial direction, which was 40 meters per second to the left, will be negative for me. 0.15 times 90, which would give me 13.5 kg meter per second or Newton seconds. Okay? So always remember, the direction thing is something that trips people up, okay? That's why I didn't include it at the start, to see whether you can catch that by yourself. This here, this negative 40 is important. You need to always consider direction when considering momentum. That's one of the most common mistakes when it comes to momentum. Okay? So now that we know it's 13.5 Newton seconds, what do we need? We need to find the force. Okay? We need to find the force. So we know that this is 13.5 Newton seconds. Imagine we're given that the time is 0.002 seconds. How would you find the force from that? So 13.5 Newton seconds, that's your impulse, is equal to force times delta time, right? So 13.5 Newton seconds is equal to force times 0.002 seconds, and force is equal to 13.5 newtons divided by 0.002, because the seconds cancel out, right? Seconds, which would give you about 6,750 newtons. Okay? And that's how you do impulse problems. You'll often get asked to switch between force delta time as well as mass times velocity, the delta momentum. And the key thing to remember is incoming velocity can change in different directions. Now, because we're going to be going over this coming up in the later units, okay? We need to understand impulse as an area, okay? Whenever kinematics, you remember how the area under acceleration was delta v, the area under v was displacement, or delta p. What's the area under an impulse graph? So here, if you have an impulse as force versus time, right? If you add force here, and as a function of time, so basically, as your time goes down, how does your force change? So if you multiply this to find the area of this, what would it be? We'd have a force units times time units, which gives us impulse, right? And if we imagine that we start at 0, this is just delta t as well. So impulse. That's how you find the impulse as an area, okay? You need to look into it right now because we'll be going into it in more depth coming up. But just remember that. Okay, so now let's try solving some problems using that. So J, which is your impulse, is your force times delta time, okay? If I want to find my impulse from this, how can I do that? A 5 Newton force acts for 7 seconds on a 2 kg object. Okay, so 5 newtons here, 7 seconds here, right? So my J is 35 kg meter per second, or 35 Newton seconds. Okay, and we know that J is also equal to delta P, so 35 kg meter per second has to equal delta P, which is mass times velocity final minus mass times velocity initial. And in this case, that would be 35 kg meter per second is equal to mass, factor mass out, velocity final minus velocity initial. Mass we know to be 2 kgs, right? So we can erase that and we can get 2 kgs here. Velocity final minus velocity initial, what's that? Velocity final, we don't know. Velocity initial is at rest, so it's going to be 0 meter per second, right? Because it starts from rest. So it's 2 times velocity final is equal to 35. The kgs can cancel out. You're left with velocity final is meter per second here. 35 divided by 2 meter per second, or 17.5 meter per second. All right, and that's how you do it. So now let's look into some more impulse problems. A force of 10 newtons acts for 3 seconds. Find the impulse. Well, that's pretty simple, right? J is just force times delta time, which in this case would be 10 newtons times 3 seconds, or 30 newton seconds. A 2 kg cart speeds up from 3 meters per second to 8 meters per second. Find its change in momentum. So change in P is just P final minus P initial, right? P final here is mass times velocity final minus mass times velocity initial. So it's 2 times 8, right? Kg meter per second minus, so I'm not including my units here because I know my final units are going to be in kg meter per second, but always make sure to include those, okay? Because you can get a lot of points off if you don't. So 2 times 8 minus m, which is 2, times velocity initial, or 3. And this should give you 2 times 8 minus 3, right? Which is 2 times 5 and 10 kg meter per second, or Newton seconds. Newton seconds. Okay. So yeah, 16 minus 6, yeah, okay. A 0.06 kg tennis ball goes from rest to 30 meters per second during a 0.005 second serve. Find the average force. So J, our impulse, is our delta P, right? And it's also equal to force times delta time. So we need to find our force. So I'm probably assuming that this will be what we'll be using here. Delta P is mass times velocity final minus mass times velocity initial. That's going to be equal to our force times our change in time. Mass is 0.06 times velocity final, which is 30 meters per second. So kgs here. Minus, it starts at rest, right? So it's 0 here. Is equal to force, which is, we don't know, times 0.005 seconds. And this should give us about, let's see here, 0.006, so 0.06 times 30 divided by 0.005. So about 360 newtons of force. Okay. A 1000 kg car going 20 meters per second is brought to rest in 0.5 seconds in a crash. Find the average force. Okay, so same situation here, right? J, our impulse, is delta P, which is equal to force times delta time as well. So delta P, mass times velocity final minus velocity initial. So if you don't understand where I got this from, delta P is just P final minus P initial, right? This is mass times velocity final. This is mass times velocity initial. So I can just factor out the m and make it the velocity final minus velocity initial. So m times velocity final minus velocity initial is force average. So this force is just a denotion, right? The force isn't going to always be equal. That's the thing about impulses. The forces rises and decline during different points in the collision. But for our sake, we're going to assume they're going to be the same, okay? Force average times time, delta time, which is 0.5 seconds, right? Okay. So mass here, 1000. So velocity initial is 20 meters per second. Velocity final is 0 because it's brought to rest, right? 0 minus 20 meters per second should be kgs is equal to force average times 0.5 seconds. So it's going to be 1000 times negative 20 divided by 0.5. Okay, or approximately negative 40,000 newtons. So the negative doesn't have a meaning by itself, it's just that it acts in the opposite direction to the car's motion, okay? Because if the car is going in this way, it makes sense that if it crashes into something, that something is going to exert a force this way, right? That's what's going to make it feel the impulse here. Okay, so yeah, it just means opposing. Alright? And the next video we'll be going over the force-time trade-off, which is a very interesting facet of impulse, as in, instead of having a higher force, you can have a higher time. And that explains a lot about why cars have crumple zones, as well as why egg drops are a common high school physics project, because it shows this principle. We'll dive deep into it in the next video, okay? Stay tuned and give me a like and subscribe so I can help you and continue helping others.